A set of vectors in an inner product space is orthogonal when every pair of vectors in that set is orthogonal. If in addition, each vector is a unit vector, then we say the set is orthonormal. Furthermore, if S is a basis, then it is an orthogonal basis or an orthonormal basis, respectively. What we want to do is show that this given set is an orthonormal basis of R3. So, first thing we need to do, let's show that it is actually a basis. Right, so we set up our matrix. And what we now want to do, remember, is row reduce this. If we can get the identity matrix out of this, then we're done. We will have shown that this is a basis. So let's go ahead and set up our matrix. That's actually not what I wanted to do. So do this. RREF. So we had 1 over square root of 2, 1 over square root of 2, and 0. Oh, I'm sorry, that was a column, not a row. Negative square root 2 over 6, and then 2/3. Then we had 1 over square root of 2, square root 2 over 6, negative 2/3. Then we had 0, 2 square root 2 over 3, and 1/3. And there we go, we have the identity matrix. So our set S defines a basis. For R3. Now what I want to do is show that the set is orthogonal. So what we have to do is take each pair of vectors and show that they are orthogonal. So take the inner product of each pair and show we get 0. Well, this is going to be under this standard inner product. So first, let's do 1 over root 2, 1 over root 2, 0. Dotted with negative root 2 over 6, root 2 over 6, 2 root 2 over 3. All right, so standard inner product, we're going to get negative 1/6 plus a sixth plus 0, which is 0. Second pairing, we'll have 1 over root 2, 1 over root 2, 0, with 2/3, negative 2/3, and 1/3. This will give us 2 over 3 root 2 minus 2 over 3 root 2 plus 0, which is again 0. Third and final pairing, negative root 2 over 6, root 2 over 6, 2 root 2 over 3, with 2/3, negative 2/3, and positive 1/3. So we'll get negative 2, negative 2 root 2 over 18. Don't know why I'm writing it that way. Negative 2 root 2 over 18 minus 2 root 2 over 18 plus 2 root 2 over 9. Now, if you look at this, this is actually negative root 2 over 9. This is negative root 2 over 9. Add them together, we're going to get negative 2 root 2 over 9. Added that with 2 root 2 over 9, this will indeed give us 0. Each pairing of vectors is orthogonal. To show that it's orthonormal, we have to show it's orthogonal, which we just did, and show that each vector has length of 1. All right, so let's start with length of the first vector. It would be the square root of the inner product of this vector with itself. So it would be square root of a half plus a half plus 0, right? Because it's 1 over root 2 times 1 over root 2, which is 1 over root 2 squared. And it's going to be like that for each component. Well, this is just the square root of 1, which is 1. Next up, negative root 2 over 6, root 2 over 6, 2 root 2 over 3. So we're going to have square root of 2 over 36 plus 2 over 36 plus 8 over 9. This is the square root of 9 by 4. And so 8 by 4 is 32, added to 4, 36 over 36, which is indeed 1. And the final, 2/3, negative 2/3, and 1/3. This is the square root of 4/9 plus 4/9 plus 1/9, which is the square root of 9 over 9, which is also 1. So this set is a basis. Each pairing of vectors is orthogonal, and each vector has length 1. Hence, this is an orthonormal basis. if the set of vectors v1 through vn is an orthogonal set of non-zero vectors in an inner product space, then the set is linearly independent. Right, so what we want to show is that C1V1 plus so on and so forth plus CNVN equaling 0 has only trivial solution, right? Remember, that's what it means for a set of vectors to be linearly independent. Well, take the inner product of both sides with the vector vi. Right? Then this is true for all vi and s. Using properties of inner products, we can write right, but 0 with vi is just going to give us 0. Since S is orthogonal, we have to have Vj with Vi equaling 0 for all j not equal to I. Therefore, what we now have is Ci, Vi with Vi has to equal 0. But this has to imply that Ci is equal to 0, right? Because this inner product can't be 0 because Vi is not equal to 0 for all I. Right, because the set is a set of non-zero vectors. Therefore, the only solution is all the c's are 0, which is what we wanted to show. And so our proof is complete. So as a consequence of this, if V is an inner product space of dimension n, then any orthogonal set of n non-zero vectors forms a basis for V. So this is a consequence of the theorem we just proved, as well as a theorem that we proved in the study of vector spaces. We now look at the Gram-Schmidt process. So this is a process that allows us to take any basis and convert it to an orthogonal basis or an orthonormal basis. So the theorem itself states, let V be an inner product space and let W be not equal to the 0 subspace, be an n-dimensional subspace of V. Then there exists an orthonormal basis T for W. Much like when we looked at the REF and RREF theorems, the proof of this theorem is our actual process. So start with a basis. All right, so we're going to start with a basis S for W. Start by selecting any vector from S, say U1, and call it V1. All right, so we're going to take U1 and just say, okay, there's our V1. We now want to look for a vector V2 in W1 equals the span of U1, U2. That is orthogonal to V1. Now, what we can do is we can write V2 has to equal A1U1 plus A2U2, right? Because it's in the span of those two vectors. But we said that U1 is V1. What we now need to do is determine the constants A1 and A2. So that the inner product of V2 with V1 is 0. So what we'll wind up with 0 is equal to A1 times the inner product of V1 with itself plus A2 times the inner product of U2 with V1. Since we know V1 can't be 0, we have the inner product of V1 with itself being non-zero, which means we can divide by it, and we get A1 is equal to negative A2 times the inner product of U2 with V1 divided by the inner product of V1 with itself. We're allowed to choose any non-zero value for A2. So pick A2 is equal to 1. Then we find that A1 is negative inner product of U2 with V1. I'm sorry, I missed a... No, that's right. V1 with V1. Right, so this is our A1. Right, we said A2 is equal to 1, so plug in those two values back in up here. What we find is, therefore, V2 is U2 minus inner product of U2 with V1 divided by the inner product of V1 with itself times V1. What we now have is an orthogonal set v1, v2. Which is a subspace. It's contained in W. Now we look for a vector v3 contained in W2 equals the span of U1, U2, U3. That is orthogonal to both v1 and v2. Now, notice that W2 is also the span of v1, v2, and u3, right? Why is this? Well, we just wrote v2 as a linear combination of u2 and v1, but v1 is equal to u1. So what we did was we wrote v2 as a linear combination of u2 and u1. Hence, it's still in the span of these three vectors, right? And since u1 equals v1, we get just v1. So these two are identical, right? If a vector is in the span of u1, u2, u3, it has to also be in the span of v1, v2, u3, because both v1 and v2 are linear combinations of u1 and u2. Thus what we have is v3 is in this span, so we can write v3 as b1 v1 plus b2 v2 plus b3 u3. And much before, we find constants b1, b2, b3, so that the inner product of v3 with v1 is equal to 0, and the inner product of v3 with v2 is equal to 0. So this gives two equations. 0 is equal to b1 times v1 with v1 plus b3 times the inner product of u3 with v1, right? And this is because v2 with v1 would give 0, right? Because v2 and v1 are orthogonal already. We also get 0 is equal to b2 times the inner product of v2 with v2 plus b3 times the inner product of u3 with v2. Solving each of these yields that b1 has to equal negative b3 times the inner product of u3 with v1 over the inner product of v1 with v1, and b2 has to equal negative b3 times the inner product of u3 with v2 over the inner product of v2 with v2. Since we can set b3 as any non-zero number, set b3 equal to 1. And so what we get is b1 equals negative inner product of U3 with V1 over the inner product of V1 with V1, and B2 is equal to negative inner product of U3 with V2 divided by the inner product of V2 with V2. Therefore, what we find is V3 is U3 minus the inner product of U3 with V1 over inner product of V1 with V1 times V1 minus the inner product of U3 with V2 over the inner product of V2 with V2 times V2. We now have an orthogonal set V1, V2, V3 that is contained in W. If we continue in this manner, right, what we will find is an orthogonal set call it T star equal to V1 through Vm that is contained in W by Theorem 1. T star defines a basis for W. Setting Wi equals Vi over the norm of Vi, right? So basically just normalize every vector in T star. We get an orthonormal basis. T equals W1 through Wm, which is exactly what we wanted. So the proof and method are complete. We will now use the Gram-Schmidt process to orthonormalize the basis 1x squared of P2 under the inner product defined by inner product of P with Q is the integral from -1 to 1 P of x times Q of x dx. Right, so remember the Gram-Schmidt process. First thing we do is set V1 equal to the first element of our basis. So we set V1 equal to 1. Then the process says that our second vector in orthogonal basis, V2, is equal to the second vector in our basis, x, minus U2, inner product of U2 with V1, over the inner product of V1 with itself times V1. So now all we have to do is find these two inner products. So first, let's find the inner product of x with 1. This is going to be the integral from -1 to 1 of x times 1 dx. All right, so that'll be x squared over 2 evaluated from x equals -1 to 1. And that is 1/2 minus 1/2, which is 0. These vectors are already orthogonal. Now, we are going to need the inner product of 1 with itself, right, when we go and divide by the norm. So let's go ahead and calculate that anyway. be the integral from -1 to 1 of 1 times 1 dx, which equals x evaluated from x equals -1 to 1, right? So that's 1 minus -1, which is 2. What we wind up with now is v2 is equal to just x, right? It'll be x minus 0. Right? Now v3 would be u3 x squared minus the inner product of x squared with our v1, which is 1, right, over the inner product of 1 with 1 times 1, and then minus inner product of x squared with x over the inner product of x with x times x. Well, we already have the inner product of 1 with itself, right? So there's only 3 we have to find. The inner product of x squared with 1. So that'll be the integral from -1 to 1. X squared times 1 dx. This is x cubed over 3 evaluated from -1 to 1. We get a third plus a third. That's 2/3. We need the inner product of x squared with x. And so that's the integral from -1 to 1. X squared times x dx. So we wind up with x to the 4th over 4 evaluated from -1 to 1. All right, and that is 0. And again, in the long run, we're going to need x with x, so might as well just do it. -1 to 1. X times x dx, which is the same as the inner product of x squared with 1. Right? We get the integral from -1 to 1 of just x squared, so that's going to wind up being 2/3. Therefore, v3 is x squared minus, right, 2/3 divided by 2/3. I'm sorry, 2/3 divided by 2, which is just 1/3 times 1 minus 0 times x. So we're left with x squared minus a third. And let's just go ahead and calculate that inner product with itself. All right, so we're going to wind up with the integral from -1 to 1 of x to the 4th minus what, 2/3 x squared plus a 9th. X to the 5th over 5 minus 2/9 x cubed plus a 9th x. Right, evaluate from -1 to 1. All right, so what do we wind up with? We wind up with a 5th minus 2/9 plus a 9th, right? So a 5th minus a 9th. And that -1, it's going to be the opposite. So it's actually going to be double that. So we're going to get two times a 5th minus a 9th. Right? So that's what? 9 minus 5 is 4, 8 over 45. All right, let's just double check that. So we're going to do integral of x squared minus a third squared. X goes from minus 1 to 1. Yes, so 8 over 45. So, orthogonal basis. T star is equal to the set of V1, V2, V3, orthonormal basis, T, 1 over the square root of the inner product of V1 with itself, which we said was 2. So 1 over root 2. Then x over the square root of the inner product of x with itself, which was 2/3. And then it is x squared minus a third over the square root of 8 over 45. So there's our orthonormal basis.